SwayamPrabha. Digital India. Educated India.
Welcome back. Now we are going to start a new topic. It's energy analysis of closed system. So this is the objectives of this particular topic. The first we are going to discuss the PDV or boundary work and some aspect of the work we've already covered. So let's go and do a formal introduction to work, particularly the boundary work. So that work is usually defined in terms of force acting through a distance. So this is a formal definition which we have used many times in simple mechanics. However, in thermodynamics it is more convenient if you can make or connect this definition to something related to process, properties, thermodynamic definition of a work, which is defined in this form, that work is done by a system if the sole effect on the surrounding, that is the surrounding means everything outside to the system, could be the raising of weight. So essentially what it means that the effective work done by a system to the surrounding can be represented as effective raising of a weight, even though we may not directly use any weight. So the definition says that only the effect could be raising of a weight, but does not say specifically that we have to physically take a weight. Okay, so we will try to explain these aspects by taking an example. We already know that work is a form of energy in transit, that means it is recognized at the boundary, okay, and the system do not contain work, and that is true for the heat as well. It is only recognized at the boundary. Now just take an example. Okay, this is an example of a battery motor which drives the fan. Now if you look at it carefully at the boundary, if you ask the question whether the work crosses the boundary, or for that matter, is there any work done for such a system, and how do you explain, because you cannot even see that the force effectively has acted through a distance. So what you can do is you can replace this fan by a system, replace with pulley and weight, and then once the motor drives, it's essentially raise this particular weight. So the sole effect of this particular system work acting on the surrounding is the raising of this particular weight. Okay, so essentially this is how we are going to analyze the thermodynamic work. So let's take specifically a system here. This is a system where you have F external applied to ideal frictionless piston, okay, having an area A. So this F external is basically the force should be needed by the surrounding in order to compress let us say the gas and reduce the volume by half, or this particular force will be felt by the surrounding as the gas expands. Now we can write the work done by the system by writing this the general differential definition. And this is a general differential definition of this mechanical work, which we write in this form. Okay, is external force, that is the force which is posing the resistance for this particular boundary to move, and the dl is the change in the height of the container, or rather the gas volume. So dl would be a distance typically raised here. For example, this could be a dl. So in general we defined the work in this form. Now, considering the area of the piston, the pressure, you can relate this work in terms of pressure. This could be related by in this form, P external into A dl, or in other words, this A is constant, so this is simply P external dV. Now we also have this P internal. So is this P external equal to P internal? And the answer is not necessary. Okay, there's only a specific case when P external is equal to P internal, when the system is extremely slow, or that's what we call it quasi static equilibrium. In that case, your P external and P internal are nearly equal, but one of them should be infinitesimally larger so that there is a change in the volume in a specific direction. So this is what the approximation is, quasi static equilibrium. In such case, your P internal would be same as P external, okay, and then we can write this particular work expression in this form. Now, for the case of quasi static equilibrium, we can refer this expression more formally in terms of boundary work, okay. So this we are using the same expression. Now this is again the same piston cylinder, okay, and the work associated with the movement of the gas, which does a differential amount of work, is referred to be W subscript B here, okay, which essentially means is a boundary work. And this is nothing but the same as a force into distance, okay, as seen here. Now for the case of a quasi static equilibrium, we can write F as simply the pressure into A, because P external is same as P internal in this case, and this is the expression for the boundary work which we can make use of it. Now for the case of expansion, that means when the gas expands, the boundary work will be considered as a positive as our convention, and when it persists, that means when the system does a work on the surrounding, WB or the boundary work would be positive, and when the surrounding does a work on the system, that means a compression in this case, the boundary work would be negative. So this is what the sign convention would be for such a case. Okay, so as I mentioned already that for quasi equilibrium process, the system will remain almost or nearly in equilibrium at all time, and in that case you can represent the process in this by a process path represented by this line here. Okay, this is an example where volume is expanding going from V1 till V2 in a very slow process such that the equilibrium is maintained, and thus the WB in this case can be written as in this form, which is nothing but the area under the curve, okay, and that's what it is mentioned here. Now we have mentioned it earlier during the introduction of this particular course that the boundary work done during a process depends on the path followed as well as the end point. So in this case, if you follow three different paths which is represented by path A, B, C, they will have different work, and basically the area under the curve will be different, as you can clearly see from here. So this area will be less than the other areas which is covered by the path B. So thus you have A will be having the maximum work, B will be lesser, and C will be least among the three possible paths for this particular example. Now if you consider process where you have expanded the system in the piston gas cylinder case from V1 to V2, so this will be the work done on the surrounding, that is work done by the system on surrounding. So and then you can also bring back the system to the original state by performing a work done on the system, that means surrounding is going to do a work on the system in a reverse process. So that will be from V2 to V1, okay. So this is one path and this is another path. So in this case, if we consider a system which we have described by two process, so the one, let's say we are starting from these are the final state represented by V2 here is larger volume. So this is V2 and this is V1. So initially you have gone the first process or the path is from V1 to V2, so that let's say this is our system A, okay, and then you have compressed the system back to V1, that means surrounding has worked on the system, and this is V. So the net work would be the work done by the system minus work done on the system, which essentially will simply mean the area under this particular two curve. So that is what would be the net work for a cyclic process or for a cycle, because you have brought back the system using two paths. First is you went from 1 to 2 on path A, and then you have written back to again 1 using path B, but then the surrounding has worked on the system. So essentially the total work or the net work would be simply the area or the difference between the work done by the system and the work done on the system. Okay, so let's try to do some example here. So this is an example of a piston cylinder device, okay, which initially contains this volume of air at 100 kilopascal. The temperature is already given, and the air is now compressed to 0.1 meter cube. So it's compressed such that the volume decreases in such a way that the temperature inside the cylinder remains constant. You have to determine the work done during this process. Okay, so this is the process path. So you have P, and essentially you are at 1 at higher volume, and you are compressed it, keeping the T0 or the temperature constant to T2. So naturally, if you think about the boundary work, this should be simply the work done on the systems. So, but let's do thorough calculation here. So we'll assume this will be quasi equilibrium process, okay, and we are assuming air to be ideal gas, because we have to make use of some equation here, equation of state in this case, and we can write ideal gas in this form. The equation is written as mRT, okay. Since the temperature is constant, that means T is equal to T0. This is nothing, is constant, the mass doesn't change in this case. Your R is constant and T0 is constant. So PV is nothing but some constant. So we can write P as C by V, right. Now what is the boundary work? Boundary work is 1 to 2 PdV, and this we can write as C by V dV, or C ln V2 by V1. Now what is C? C can be written as P1 V1. So this is nothing but P1 V1 ln V2 by V1. Now you can plug in the values which are given already to you, because you know the pressure, you know the initial volume, and you know also the final volume. So let's try to do that. So this is 100 kilopascal, 0.4 meter cube, ln 0.1 by 0.4, and this is minus 55.5 kilojoule. Now what you have obtained is the value, but there is a negative sign here. So what does that mean? It means that the work, because the expression which we have used is basically the work done by the system. So essentially the negative sign represents that the opposite effect is there. That means there is a work done on the system. So our assumption is not right, and hence with the negative sign indicates there is a work done on the system. Okay, so this is how we are going to solve a simple problem. So this would be a simple compression, which is means negative sign represent work done on the system. Okay, so let's try another example. This example is again related to moving boundary, but it will provide important relevance of considering external force. So here is a system in which the piston of mass MP is initially held placed by a pin. The gas inside the cylinder is initially at P1 and the volume is V1. Okay. Now the pin is released, and what we have to calculate is the work done by the system. Once you take out the pin, the forces are not balanced, and effectively the piston will accelerate until it reaches to the mechanical equilibrium where the pressure outside and inside are same, or the forces outside and inside are same. What is the external force on the system? So external force is F, and so the P external in this case is going to be F external divided by A. So that would be your P0 plus the weight of the piston MPG by A. Now so this P external will not be same as P1. So if P1 is greater than P external, which let's say we assume that then the piston will move upward. Okay, the piston will move upward at a finite rate. Okay. Okay, so in this case the work done would be against the force which is resisting the movement of the boundary. Okay, so what is the force which is resisting the movement of the boundary? It's basically F external. Okay, so we will be writing this W in terms of P external dV. Okay, So this is the effective work, okay, and so this would be the work done by the system against the force resisting the boundary movement. Okay. Now since P external is fixed, because your P0 is fixed and the weight is fixed, the value in this case is going to be simply P external V2 minus V1. Now if P1 was lower than P external, then of course the piston would move downward. So that was the exercise which we wanted to do in order to understand the moving boundary concept. In the next lecture we will continue with this, explore a little more with certain example. So, I will see you in the next lecture.